And it's simpler to actually implement in the custom fabric, since we're receiving 8 channels simultaneously. There's no way we can process that in a processor. And the FFT was implemented in Microblaze. Was done by Sam Harkness. It was his summer project. And frequency detection and parallel DOA were implemented in Microblaze as well. So the software-based implementation, the main thing we need to get out of this one is that it's a long sequential process that we have to go through. And then for the 8 channels, we have to go through this sequentially. And then once we get all of the information, we can calculate the DOA. So it's a lengthy process. So that's, this table shows the result. I'm going to go through the results in next slides. So if the font is small, that's fine. It just like shows the big picture of the latency, resource estimation for both the hardware. I looked at the floating point, fixed point, as well as in the Microblaze. Yeah. So looking at the single channel FFT, hardware versus software, the time required to perform the FFT in hardware is 34.3 microseconds. The software implementation for single channel was 100,000 microseconds, which is 100 milliseconds. So the hardware is almost like around 3,000 times faster, and it's 45% smaller. Again, this is only for one channel. So looking at all 8 channels together, the hardware still performs the transform in 34 microseconds. The software needs 800 milliseconds to perform the complete transform, because it will do that sequentially. The hardware has the ability to perform all channels simultaneously. It takes the same amount of time. So the hardware is 24,000 times faster than the software, but since we implemented 8 channels, we needed more resources, so it's, the software ended up being 4 times smaller. The frequency detection for a fixed point, the hardware implementation requires 10.3 microseconds to perform that. The software, 1 millisecond. So it's like 100 times, the hardware is 100 times faster, and the hardware is 100 times smaller. And when we compared the resource utilization, we compared with the entire Microblaze. It's well, the Microblaze also, it doesn't only do for example, the frequency detection. All these resources are used for FFT, frequency detection, and DOA estimation. But since it's fixed for the Microblaze, then we needed some sort of comparison to look at.
For these estimates, what's the clock rate on the Microblaze?
It's 100 megahertz.
Okay.
Yeah. Sorry, and the FPGA is also running at 100 megahertz. So
yeah, it's the parallel serial thing.
And do you have I'm trying to, in the back of my mind here, figure out the real-time aspect of this. So you have the time to accumulate 1,000 samples at 25 megahertz? And then you run the processing.
So, yeah, this time is independent of how long do we need to do the sampling. So we do the sampling at the beginning, and then once that's done, we fire the rest, like the rest.
Right, I'm trying to see if the total of all your processing is going to fit within the time it takes to acquire the next 1,000 samples. So is it feasible with hardware that you get this done before the next wire runs?
In the hardware implementation, it will fit entirely. We can see the overall performance of the hardware. So yeah. So for the DOA estimation, running the parallel algorithm, it's the time required in hardware is 1.7 microseconds. For software, it's 300 microseconds. So the hardware is 180 times faster, and it's 8 times smaller. So for the complete system, it requires the hardware to detect the direction of arrival or estimate the direction of arrival. It takes it 46 microseconds. In the soft processor, it takes it 839 milliseconds. So it's 18 times 10,000 times faster. And as we looked at the results previously, mainly due to the FFT because it's the longest process that's needed. And then the software is 4 times smaller than the overall hardware system. This time doesn't include the time to sample, but as I recall, the time to acquire a complete sample, I think it's more than 46 microseconds. Well, when this system was designed, we were running on, previously at the beginning, we were running on a slow, we used the slow ADC board, which was sampling at 20 kilohertz. So, but now when we moved into the new board, I think
40 microseconds for 25.
Oh, for 40 microseconds? So, yeah, well, then there's a small wait. But the thing is, once the FFT is done, we can actually start sampling again since we don't need the previous samples because we already used them or we already loaded them into the FFTs. So we can start the sampling again. And that's, you're going to see this optimization when I talk about the implementation of MVDR. So to come up with the best balance between the hardware and the software implementations, since hardware takes a long time to implement it, we found that to have the ADC driver and the FFT and the frequency detection all implemented in hardware, since they're already optimized, and especially FFT is provided by Xilinx, and it's working, then it makes more sense to have that working in hardware and then perform the algorithms in a microblade, since microblades gives us the ability to develop code or implement DOA estimation algorithms in a fast time. And we looked at the Bartlett DOA. It was 300 or 180 times faster than the hardware, so it's not, it's 300 microseconds, so it's a trade-off that we can take. So looking at the performance, the time needed to complete the DOA estimation in hardware 46, in hybrid it's 1.3 milliseconds. So the hybrid is 30 times slower than the hardware, but it's 620 times faster than the software implementation. The hybrid system is larger than both the hardware and the software implementations due to we needed to have a microblade as well as having the other components needed to perform the FFT and DOA estimation, the frequency detection. So the hybrid system, it balances development time. So by using cores, generated cores, and the processor, we have the fastest development time we can get. And backend flexibility, we can do whatever post-processing we need or try testing different algorithms on the hardware. So now I'm going to talk about the MVDR, DOA estimation. In here, MVDR stands for Minimum Variance Distortionless Response. Well, here the goal is to minimize the output power of the system except in the direction of the desired signal. And then the estimated DOA is represented by peaks in the power spectrum. And MVDR has way higher resolution than Bartlett method. So the MVDR DOA estimation consists of sampling and then doing FFT and frequency detection just like in Bartlett. And then we need to build the R matrix, which is a covariance matrix, and then calculate the inverse of that, and from that calculate the power. Just as we saw in the equation, we need to calculate the inverse of that to get the power. So perform, in order to get good averaging, perform 128 rounds of sampling as well as 128 rounds of FFT. So the hybrid implementation for the system, the main difference here is that we moved all the interfacing signals into another component, the system controller. So it actually triggers each